Hello, today we'll explain about the minimum spanning tree or Prim's greedy algorithm. Before we explain the minimum spanning tree, let's explain what are greedy algorithms. Greedy algorithms are problem-solving strategies that make locally optimal choices at each stage in hopes of finding a global optimum. These algorithms overall help to choose the optimally local available solution, disregarding if the solution chosen will lead you to the optimal solution or not. Hence, they are considered greedy algorithms. Now, let's head into explaining what a spanning tree is. A spanning tree is a graph tree that has edges connected all around each other. This is a visual demonstration of all the nodes labeled from A to F with edges connecting it all around. This is a spanning tree. A minimum spanning tree or a minimum weight spanning tree is a subset of this spanning tree. Look at this is the spanning tree, and this is the minimum spanning tree of it. It is a subset taken of it that holds on and ensures that there are no cycles all around the edges. All edges have contain minimum weights all around each others and no loops. Let's look at an example of how we can construct a minimum spanning tree from a spanning tree. Here we have the nodes, a graph tree containing nodes from A to F with the weights all around it. Of course, these are the rules that we mentioned before. All the vertices should be connected, and there should be no cycles in the minimum spanning tree, and of course it should have the minimum weight on each edge. First of all, we choose a starting point. Let's pick A, for example, as a starting point. After picking A, we choose the weight that has the minimum weight around it from A to any other node, of course, which is 2, from A to B. We select it and draw it. Next, we pick the minimum one overall, which is from B to D, which is 1. So we draw the path. Next, we find the next best one, or the minimum, which is 2, from D to E. Now you'd be tempted to pick 3, since it's the least. But no, you shouldn't pick it, because this revokes a rule that we stated earlier, that there shouldn't be any cycles in the minimum spanning tree. So we pick the next best option after 3, which is 4, from B to G. Next, we pick the next best option, which is 1, from G to F. As a result, we have a minimum spanning tree with no cycles or no loops around it, and it contains the minimum weights or edges of the minimum spanning tree, which add up to 10. Now, for the code of the pseudocode for the algorithm itself, it contains 3 variables needed: num vertices, selected, and remaining vertices. The num vertices, of course, stores the number of vertices in the graph itself. The selected vertices is a list that starts with the first vertex or the first node or the start node, and the remaining vertices contains a list of all the other nodes. It loops around the remaining vertices and picks a variable minimum edge and sets it to a very high value. Then it loops to the selected vertices, and then inside of the loop it loops through inside of the loop, which loops to the remaining vertices, and then picks and chooses each graph. Is it less, or the edge represented, is it less than the minimum edge? And then if it is, it initializes the minimum edge variable with the edge or the weight itself, and it puts these 2 vertices and stores them in the minimum edge vertices. After finishing the 2 loops inside, it appends it to the selected vertices list and removes the 2 vertices from the remaining vertices. Now this implementation assumes that you have using an adjacency matrix as your data structure. This is the representation or the visual representation, and this is the code for the adjacency matrix representation. For the analysis and time efficiency of the algorithm, it starts off with the outermost loop, which loops through the remaining vertices, assuming in the worst case it loops from 1 to the total number of vertices, which is from 1 till V. Next, inside we loop through the remaining selected vertices, which again, assuming in the worst case, from 1 till V, and of course the same scenario happening on the inside, with the inside and then the basic operation happening is the comparison of each weight to the minimum edge, which gives us this algebraic summation. Next, on solving it, we evaluate the innermost one, which again was a rule according anything looping from 1 till V with the operation 1 will be 1 times V, which gives us V. Then we initiate the same rule again, since it's a constant. From 1 till V, of course, will be V times V, giving us V squared according to this rule. Next, we evaluate the same thing again, which gives us V squared times V, which will be V cubed. Hence, the big O for this one is big O V cubed. Thank you for listening.